Welcome to The Explainer. All right, today we're tackling one of the biggest, most mind-bending ideas in all of science, Albert Einstein's theory of relativity. So get ready, because we're about to see how one person's imagination completely rewrote the rules of reality and changed how we see space, time, and gravity forever.
So let's just jump right in with a question that gets to the very heart of this, and it's a huge one. It challenges our most basic gut feeling about the universe. That my now is the same as your now. That time is this universal clock, just ticking away for everyone, everywhere at the exact same rate. Well, as we're going to see, Einstein proved that this idea, as comforting as it is completely wrong.
To really get why Einstein's work was such a bombshell, we need to rewind a bit, back to the late 19th century. Because honestly, physics was in a bit of a crisis. The two main pillars of science, the laws that described everything from a falling apple to a flash of lightning, were basically at war with each other.
Okay, so on one side of the ring, you've got Isaac Newton. His rules were simple. They made sense. If you're on a train that's moving and you throw a ball forward, the speed of that ball relative to the ground is just the train speed plus your throwing speed. Easy. But then, in the other corner, you have James Clerk Maxwell's equations for light. And they predicted something really weird. They said that light from that same train's headlight travels at the same speed, the speed of light, c, no matter how fast the train is going. The speeds just don't add up. One of them had to be wrong.
And look, this wasn't some tiny little discrepancy they could just sweep under the rug. This was a full-blown crisis, a deep crack in the very foundation of physics. The universe couldn't play by both Newton's rules and Maxwell's rules at the same time. This is the stage that was set for a young, totally unknown patent clerk named Albert Einstein to step in and rethink, well, everything.
Then, in 1905, what we now call his miracle year, Einstein drops his solution on the world. He called it the Special Theory of Relativity, and he built the whole thing on just two incredibly simple but world-shattering ideas.
Here they are, the two postulates that changed everything. The first one makes sense. The laws of physics work the same for everybody moving at a constant speed. Whether you're standing still or cruising in a spaceship, your physics experiments will turn out the same. But that second one, wow, that was the real bombshell. Einstein made a choice. He said Maxwell was right. The speed of light in a vacuum is the same for absolutely everyone. It's the ultimate unbreakable cosmic speed limit.
And this right here is where reality starts to get wonderfully strange. Because if the speed of light must be the same for everyone, then something else has to give. I mean, think about it. Speed equals distance divided by time. If the speed part of that equation can't be broken, then the distance and time parts must be flexible. Einstein realized that space and time themselves have to stretch and shrink, all to protect this one constant, the speed of light.
So, what happens when you follow this idea to its logical conclusion? What are the consequences that just ripple out from this one radical thought? Well, let's just say things get a little weird.
First up, time dilation. It's exactly what it sounds like. Time itself can stretch and slow down. The faster you zip through space, the slower your clock ticks compared to someone who's just standing still.
And I really want to stress this. This isn't some kind of optical illusion or a trick of the mind. This is real. It's a measurable physical effect. We've actually proven it. We've flown super accurate atomic clocks on airplanes around the world, and when they land, they are measurably behind the clocks that stayed on the ground. Time literally ran slower for them.
And it's not just time that gets warped. Space itself is flexible. To someone watching from the sidelines, any object that's moving will actually look shorter in its direction of motion, and the closer it gets to the speed of light, the more squished it appears.
All of these strange effects on space and time, they lead us directly to the most famous equation in all of science. You see, as something gets closer to the speed of light, not only does time slow down for it and its length contract, but its mass actually increases, making it harder and harder to speed up. This realization led Einstein to a deep, profound connection between mass and energy.
What this little equation is telling us is something incredible. Mass and energy are basically the same thing, two sides of the same cosmic coin. They can be converted into one another. And because that c² part, the speed of light squared, is such a gigantic number, it means you can get a tremendous amount of energy out of a teeny tiny amount of mass. And just like that, you have the foundation for the entire nuclear age.
But here's the thing. As revolutionary as that 1905 theory was, it wasn't the full story.
It was special because it only worked for a special case: nice, constant, unchanging motion. There was a big piece of the puzzle missing.
You know, the real world isn't all about just cruising along. Things speed up, they slow down, and more importantly, there's gravity. Here was the issue. Newton said gravity was an instantaneous force. If the sun just vanished, poof, we'd feel the gravitational effect immediately. But Einstein's new rule was that nothing can travel faster than light, not even information about gravity. So Newton's idea of gravity just didn't fit. Einstein knew his work wasn't done.
So for the next decade, Einstein wrestled with this problem. And in 1915, he revealed his masterpiece, the General Theory of Relativity. And his new vision for gravity was, if you can believe it, even more radical than his first theory. His big aha moment came from one of his famous thought experiments. Imagine you're in a sealed rocket ship, way out in deep space. If that rocket starts accelerating upwards, you'll feel yourself pushed to the floor, right? Well, Einstein realized that feeling is completely, totally indistinguishable from the feeling of just standing still on Earth, being pulled down by gravity.
And that led him to his truly grand idea. Gravity isn't a force at all. It's not some invisible rope pulling things together. It's the shape of the universe itself. Think of it like a bowling ball on a trampoline. It makes a dent, a curve in the fabric. Einstein said massive things like the sun do the exact same thing to the four-dimensional fabric of spacetime. The Earth isn't being pulled by the sun. It's just following the straightest possible path through the curved space that the sun has created.
So that's really the core difference between his two big theories. Special relativity is the rule book for a flat, unchanging spacetime. But general relativity, that gives us the whole picture, a dynamic, curved spacetime, where that very curvature is what we experience as gravity.
Okay, so at this point, you might be thinking, this is super cool, but it's all just theoretical, mind-bending stuff, right? Well, not at all. Relativity has some very direct, very essential applications that you probably use every day.
Just think about the GPS in your phone, something you use all the time. It absolutely would not work without Einstein. The clocks on those GPS satellites are moving really fast, so special relativity says their clocks should tick slower. But they're also in a weaker gravitational field than we are, so general relativity says their clocks should tick faster. Engineers have to correct for both effects. If they didn't, your GPS would be off by miles every single day. And that's not to mention its importance in everything from huge particle accelerators to understanding black holes and the expansion of the cosmos.
So, what's the big takeaway from all this? It's that Einstein completely demolished our old, comfortable view of the universe. He showed us that space and time are not just a static, boring backdrop for events. Nope, they are active, flexible players in the great cosmic drama, constantly bending and stretching in the presence of matter and energy. And that just leaves you wondering, right? Einstein's ideas led us to things like black holes and ripples in spacetime called gravitational waves, things that sounded like pure science fiction until we actually found them. So if he could show us that the very fabric of reality can bend and warp, what other unbelievable secrets is the universe still hiding from us?